Our next presenter is coming in remotely. It's Samudra Haq from George Washington University. Good morning, Samudra. It's a preliminary sizing of a micro-cathode arc thruster subsystem for operation in cis-lunar space.
Hello, everybody. I'm Samudra Haq from George Washington University. I'm going to be speaking about a potential easy-to-use electric propulsion solution for small spacecraft. And we call our system a micro-cathode arc thruster. And it is actually quite small, so it does fit the name micro, but it also produces a very accurate impulse bits in the micronewtons. So we do like to call our thruster system a micro-cathode arc thruster subsystem. And it's a great pleasure to be able to present the latest results of our research from George Washington University at the 4th International Workshop on Lunar Cubes. And I'd like to take this opportunity to thank Dr. Clark for inviting me, as well as my colleagues at different institutions who have been collaborating with us as we go towards our first space mission in 2015. And I'd like to say that electric propulsion has really been a work that has spanned almost over a century. And it actually has about the same heritage as the chemical rocket industry. There have been various technology families of electric propulsion subsystems that have been investigated, researched, produced, expanded, and then flown on space missions beginning in the 1960s onwards. But early tests were actually even earlier than that. And the three major families, electrothermal, electrostatic, and electromagnetic, in which respectively electrical energy or some other form of energy is required to heat gases, which produces pressure, which then moves the spacecraft, or a very innovative use of electric fields, which is using electric fields to accelerate the ions, but you'd have to produce the ions somewhere. And the more common varieties, which are electromagnetic propulsion systems, of which we are a small part of, but the bigger systems are perhaps pulse plasma thrusters, Hall thrusters, MPD thrusters. And what happens is the system, as it becomes much smaller, has to be able to work with a variety of components and materials, and it is really depending a lot on the behavior of those materials in the precise amounts of time and the precise amounts of energy being utilized to create the all-important spark. As I mentioned, it's been a fairly long process for electric propulsion to come to the point where I'll show you how small and how efficient they can become. And as I was doing a bit of research for this presentation, I came across Dr. Choueiri's paper, where he talks about the early pioneers who all covered the potential of electric propulsion. And they actually went ahead and created the first math models in absence of any hardware. So it's quite, quite interesting that we are many decades away from these visionaries, and we're actually now able to say back to them over time that you were right, and that we've actually created micro-propulsion systems that are smaller, efficient, and quite scalable. And while they wrote about it, we are actually doing it at this point. The 2014 time frame has been very productive for George Washington University. We have created a system of production of micro-cathode thrusters for our own research enhancements, and the ability to both model them mathematically as well as measure their output in a vacuum chamber, and also to collaborate with different partners such as the space centers of NASA and institutions such as the Naval Academy, where we are actually learning all about how to make our systems compatible with their spacecraft. And we'd like to say that in a few months from now, we will have on-orbit experiment data that will actually validate our designs and our models. And the picture on the right-hand side, lower section of your screen, actually is a unique event. Those are thrusters that were produced under guidance from George Washington University students, but produced at the Ames Research Center through their own facilities. And that's because the genesis of this technology includes a section of experiment that we did in 2013 called the Micro-Cathode arc phone set experiment. The capability of the Micro-Cathode arc thruster subsystem is well characterized by now. It's been under continuous development since about 2007 onwards, and a variety of small groups within the micropropulsion and nanotechnology lab have been working on either the thruster mechanism, either the electromagnet that is often used to accelerate the plasma jet, the control systems, the power management sections, the power switching sections, the command and telemetry functions. And at the basic level, it is an electropropulsion device that has a variable ISP depending upon what material we utilize as the thruster cathode element, either titanium or nickel at present, but there are other metals being tested. And the mass is quite compact, within half a kilogram in most cases for a generic 6U kind of frame, or a 3U or 1U even. And the efficiency is approximately 15%, and that's based on real practical measurements. The original challenges of the system for myself date back to early research that I did in 2009 and published in 2011, that any system that could satisfy the variety of applications that we needed to do, but targeted squarely to small spacecraft in all respects, would actually allow us to eventually propose a constellation of spacecraft in unique configurations and unique network architecture, essentially to provide multi-hop deep space services, if you will, wherever you want to place them, because the engines would be quite affordable and easy to utilize. The challenges were, however, quite a lot. First of all, we had to figure out the basics of how a thruster would be excited, how a thruster could be controlled precisely, because once you start scaling up systems, you become then aware of a variety of issues such as power consumption, then triggering of different channels simultaneously, or on an on-off or on-pulse or off-pulse basis. And then you have to worry about, well, how many systems do we need to drive the real thrusters? Do we need one for one, or do we need one to many, or do we need many to one, or do we need redundancy, or do we need clustering, or do we need hybrid array type of arrangements? And this has become quite a big area of interest and research for me. The net result is that from a few years ago, we were able to produce a generic testbed platform for our lab condition, and then we were able to prove at the Ames Research Lab Engineering Evaluation Laboratory a breadboard benchtop 3-channel thruster subsystem. But thanks to a lot of diligent work in selecting components and our interaction with different other engineers, we learned a little bit about the challenges of making multi-layer PCBs and using the current generation of switching regulators and compact power switches, and also the fact that most of the programming for the microcontrollers can be adapted to generate the precision trigger pulses and the precision synchronization control signals needed to have a system where you could have n number of thrusters with m channels, and you could have redundant rings of components in between. The first application of our system will be the BricsSat P mission, and the P is for propulsion. BricsSat is ballistically reinforced communication satellite. It's going to be managed and flown by the Naval Academy, and they chose to employ our thrusters in an X-wing configuration. Affectionately, there's a little sketch that goes around the group where a Star Wars fighter type X-wing has 4 engines, placed in such a manner. Their objectives in the first on-orbit demonstration will be to have the initial detumbling modes, controlled spin, and delta V operation, and we're actively pursuing the programming and the command telemetry systems development at this stage. The generic technology is scalable, and recently, with the help of the Goddard Space Flight Center and also Morehead State University, a design was created, which is probably going to be discussed at another event, or has been discussed at another event during LCW. But a 29 thruster system with a lot of spare elements of attitude control thrusters and main propulsion thrusters were calculated for the main mission of about 870 meters per second system delta V required over a fairly long number of months. So it was quite exciting to actually take the numbers proposed a few years ago and see what would happen. We actually did spend some time, mostly graduate student time, in looking at the various other proposals for flying to the moon from an Earth orbit. So here we have a patched conic approximation based on a 12-kilogram mass, and then we also have a spiral transfer, mapped out already, where assuming that our first on-orbit tests go well and we get hard data from SpaceTrack as to what our thrusters can do by themselves on an individual basis, can do in pairs, can do as in triples, and can do as a quad, or can be utilized to change their attitude, we'd be able to come back to these models and actually, come with a better confirmation of what we can achieve if we had energy on board. Because this is, after all, almost a solid-state device, though it's not really as fragile as a solid-state semiconductor system, but it's really a solid-state mechanical device. The conclusion that we reach after all of this last few years of work is that we actually could propose a standardized bus arrangement, perhaps based on the BricsSat P model or something else adapted for 6Us or 12Us or whatever. And they actually can safely take the payloads in any configuration, either as a push or a pull vehicle, or just simply an add-on propulsion assist module. Given the adequacy of solar energy in our Earth-Moon system, we should be able to spend a lot of years, if necessary, in very agile orbits. I've tried to give some references in this presentation. I'm sure you can download it. And what I'm going to ask is if anybody has a question, I would try to answer them. But if not, please do contact me, as I'm oftentimes able to just work within my current research area and try to solve the problem that you might be facing. So my email address is listed here, and I'd like to open up the floor for questions. Thank you very much. This is Samudra Hawk.